Good morning. Today we're going to talk about limiting reactants. Now when I teach this lesson, I usually give an illustration of making s'mores. Typically our family goes camping in the spring or fall, and that is something we make when we go camping. We make s'mores. So to make s'mores, you have to have 3 ingredients. You need to have chocolate, graham crackers, and marshmallows. Well, let's say that you brought enough chocolate to make 10 s'mores, but you have enough graham crackers and marshmallows to make 20 s'mores. How many s'mores can you make? Well, the fact that you only have enough chocolate to make 10 means that it doesn't really matter that you brought enough graham crackers and marshmallows to make 20. You only have enough chocolate to make 10. So you can only make 10 s'mores. After that, you'll just be making marshmallow sandwiches. So we would say that chocolate is your limiting reactant. So in a chemical reaction, you're going to learn that the limiting reactant is the reactant that runs out first, and therefore it limits the amount of product that you can produce. So it's the reactant that you run out of. It determines or limits the amount of product that will be formed. And this is opposed to the other reactants in the equation, which would be referred to as the excess reactants. In my illustration of the s'mores, the marshmallows and the graham crackers would be in excess. I would still have 10 left over after I had made all of my complete s'mores. So the excess reactants are the reactants that you have extra of. You will always have some left over. Not all of it will be used. Now to give you an example of something that you have done in class, there have been times where we put metals in acid. You might remember one time in particular that we put magnesium in acid and you saw it fizz up, you saw smoke or gas released. And then after just a few seconds, all the magnesium was gone. All of the magnesium had reacted with the acid. Well, something we didn't do is we could have taken another strip of magnesium, put it in the same acid, and we would have seen the same thing happen. And the reason why is because in that reaction, magnesium was the limiting reactant. When the magnesium had been completely eaten up by the acid, the reaction stopped. But you still had excess hydrochloric acid, so that if you were to go back and add more magnesium, the reaction would start up again. Now, I'm going to quickly go through the steps of how to determine your limiting reactant, but I'm going to go ahead and give you a disclaimer that these steps are not very straightforward. We're just going to have to jump right in and do a problem, which I will show you what worksheet in your packet you should take out for these problems. So real quickly, the steps always start with a balanced chemical equation. That's what we talked about at the very beginning of this unit. To do stoichiometry, you need a balanced equation. And then you want to do your gram to gram conversions. So just like you did on your recent quiz, you're going to convert the grams of each reactant into grams of the same product. And the reason why we're doing this is we're trying to figure out, we're doing stoichiometry to figure out how much product can each reactant produce. Just like with the graham crackers and the s'mores, if there's enough chocolate to make 10 s'mores, but there's enough marshmallows to make 20 s'mores, we are figuring out that by the fact that we can only make 10 s'mores, chocolate is our limiting. So after you convert the grams of each reactant into grams of the same product, you're going to look to see which amount of product is less, and that's going to tell you which one is your limiting. So the reactant that produces the least amount of product is your limiting reactant. And something else we're going to talk about today is how to determine theoretical yield. Theoretical yield is just theoretically, how much product should we be able to produce? And that is determined by your limiting reactant. So again, with the illustration of the s'mores, my theoretical yield is 10 s'mores. That was determined by the limited amount of chocolate that I brought with me on this camping trip. All right, so those are your steps. So I'm going to switch over now to my document camera, and we're going to just jump right in to a problem. Again, this packet is in, or this these worksheets are in your packet, so you might want to take those out now. They should be like the second or third sheet in your packet. So let's read this problem. It says nitrogen gas can be prepared by passing gaseous ammonia over solid copper 2 oxide at high temperatures. The other products of the reaction are solid copper and water vapor. So before we go on, let's go ahead and write our balanced equation. This was worded a little confusingly, but let's go back and see if we can figure out what our reactants are. Nitrogen gas can be prepared tells us that nitrogen is going to be one of the products. So how is it prepared? It's prepared by passing gaseous ammonia. So ammonia is NH3. Passing gaseous ammonia over solid copper 2 oxide. So that's your other reactant. By the way, copper 2 oxide, copper has a +2 charge, oxygen is -2, so those cancel out. So I don't need any subscripts here. So those are my reactants. I already know that the first product is nitrogen gas. Don't forget that nitrogen is a diatomic molecule. So when you write nitrogen, you've got to make sure to write a subscript of 2 next to it. And then the other products of the reaction are solid copper. And remember, copper by itself is fine. We can just leave it. And then water vapor, so just H2O. All right, so before we go any further, let's balance our equation. Starting with nitrogen, I see that I have 1 on the left, 2 on the right. So I'm going to put a 2 here. Putting that 2 there gives me 6 hydrogens. So I'm going to put a 3 here. Now putting that 3 here also gives me 6 hydrogens, but it gives me 3 oxygens. So I need to put a 3 in front of copper 2 oxide. And then lastly, to balance copper, I need to put a 3 in front of Cu. So I have 2 nitrogens, 2 nitrogens, 6 hydrogens, 6 hydrogens, 3 coppers, 3 coppers, 3 oxygens, 3 oxygens. All right, now I am ready to solve for the limiting reagent or the limiting reactant. Those 2 words can be used interchangeably. So if we read that last sentence of the problem, it says, if a sample containing 18.1 grams of ammonia is reacted with 90.4 grams of copper 2 oxide, which is the limiting reagent? So they're telling us that we are starting with 18.1 grams of ammonia and 90.4 grams of copper 2 oxide. And what I'm trying to figure out is which one of those is going to run out first. Well, you may remember from the notes that in order to determine this, I need to do a gram-to-gram conversion, figuring out how much product each of these reactants can produce. Well, I have 3 products to choose from, and if all you have to do is determine the limiting reagent, you can choose any one of these products and it'll be fine. Just make sure you choose the same product for each reactant. Whichever one is in the smallest amount, that tells you what your limiting reactant is. But we can save ourselves some time if we look a little bit further in this problem. If you look down to question number 3, it asks how many grams of nitrogen should be formed. So it's specifically asking us to find the theoretical yield of this product. So since I'm going to have to find that later, and you'll notice that the last question is also about nitrogen, that's the product that I'm going to use for my problem. So I'm going to take ammonium, 18.1 grams. And remember, before I go from grams of one reactant to grams of this product, I need to first convert this into moles. Then I'm going to set up a mole-to-mole ratio, and then I can convert my final answer back into grams. So I need to find the molar mass of ammonia. All right, so looking at our dynamic periodic table, if you need to see it, you might already have these memorized at this point. Nitrogen's mass is 14.01. Hydrogen is 1.01 times 3. Here's my work over here to the side. So that's going to give us 14.01 plus 3.03. We get 17.04. So that's our molar mass. All right, now I can set up my mole-to-mole ratio. Remember, the product that I'm putting on top is nitrogen, and the reactant that I'm putting on the bottom is ammonia. And that mole-to-mole ratio is 1 to 2. And then I can convert that back into grams. Now, to convert that back into grams, I need to know nitrogen's molar mass. So since nitrogen is 14.01 and this is N2, I'm just going to double that. So 28.02. And now I can plug all this into my calculator. Divided by 2 times 28.02. All right, and keeping with my original number of significant figures, I'm going to round that to 14.9 grams. And remember, this is 14.9 grams of nitrogen. What we just determined is the same thing that you did on your recent quiz. You just took the grams of one of your reactants and you determined how much product that would produce. We're going to do the same thing now with the other reactant. So starting with 90.4 grams of copper oxide, we need to convert that into moles first. So looking at our dynamic periodic table, copper's mass is 63.55. Oxygen's mass rounds to 16. So I get 79.55 as my molar mass. And now I can set up my ratio. Now remember, we're using the same product on top. We're still using nitrogen. And now my mole-to-mole ratio is 1 to 3. And then I'm also multiplying by the molar mass of nitrogen as my final step. All right, so this time I get 10.6 grams of nitrogen. All right, so what we just determined, again, this amount of ammonia can only produce 14.9 grams of nitrogen. This amount of copper 2 oxide can produce less than that. It can only produce 10.6. So since this reactant produces less product, this is my limiting. So the answer to question number 1 is copper 2 oxide. That is my limiting reactant. Now what we have also determined is the theoretical yield. Remember back to my example about camping? If you only brought enough chocolate to make 10 s'mores, it doesn't matter that you brought enough of the other ingredients to make 20. Your theoretical yield of s'mores would be 10. So it doesn't matter that we have enough ammonia to make almost 15 grams. The fact that this other reactant is limiting us in our production means that this is the theoretical yield. So that would be the answer to number 3, 10.6 grams of nitrogen.